Welcome to lecture 38 of the course Modeling and TCAD Simulation of Solar Photovoltaic Cell. In this lecture, we will continue the numerical solution of semiconductor equations. But in this lecture, we will mainly focus on the discretization part and then uniform and non-uniform meshing schemes. In last lecture, we have discussed the different discretization techniques, namely finite difference method, finite volume method, finite element method, their comparative performance analysis, that is merits and demerits of each with respect to others. Also, we have discussed usefulness of the numerical techniques, and in this lecture we will concentrate on finite difference method and the meshing techniques for numerical solution. And also two types of meshing, that is uniform and non-uniform meshing, will be discussed. Before going to the meshing structure, let us first discuss how good are the finite difference approximations. Because we have seen that the differential equations or the differentiation, say first order or second order differentiation, these are based on some truncated Taylor series expansion of f of x plus delta x. And in that case, we have sometimes approximated after second term, we have approximated sometimes after third terms in the Taylor series expansion. But we have to have a knowledge how the errors are occurred due to these approximation. So let us first do the Taylor series expansion of x plus delta x. We know function of x plus delta x that can be written in this form, that is f x plus delta x is equal to fx plus some delta x amount f dash x. This is the actually del f del x, the first order derivative, plus delta x whole square by 2 factorial f double dash x, that is del square f del x square, plus delta x cube by 3 factorial f triple dash x, third order differentiation. In this way it is going on. And the minus side also, that is fx minus delta x, this will be negative sign, this will be negative sign, and the 5 factorial, so these odd factorial terms will be negative. Anyway, so in the same expression, we have shown how x plus delta x or x minus delta x can be expanded by using a Taylor series expansion. Now, say with forward formulation, what I am meaning the forward formulation, because we have defined the differentiation in forward direction first. So what happens if we use this expression for del f del x, that is the forward difference approximation of the first order derivative del f del x that we have discussed in last class, f of x plus delta x minus fx by delta x. This is the definition of del f del x. If we put this value here, so what will happen? F of x plus delta x minus fx from this Taylor series expansion by delta x, that will be in the expansion, it will be 1 by delta x because delta x is introduced here. So basically we have taken the fx term in the left hand side and then divided this by delta x. So 1 by delta x into delta x f dash x plus delta x whole square by 2 factorial f double dash x, and in this way. And here we have neglected higher order term after the second term. So if we simplify, the delta x cancel with the first term in the right hand side now. So this becomes f dash x plus other terms we have neglected. So what amount of error we actually neglected? Because say delta x, if we divide this delta x square whole square by delta x, this will be delta x. So delta x by 2 factorial into f double dash x term, that is neglected, that we have neglected this term. We have neglected this term also, there delta x cube divided by delta x, this delta x coming from here, so delta x is square term. So all the term related to the delta x and higher order square of the delta x are neglected. So maximum error, that is of the order of delta x. Why? Because delta x is neglected here and from the second term, and delta x square neglected in the third term, but delta x square is always much less than delta x square, because delta x is less than 1. Delta x is very small value. So any number below 1, if you take square, cube, so it will be further less, going to less and less. That's why this can be written as the neglected term, as can be treated as the order of, this O stands for order of delta x. So error is introduced, that is of the order of delta x. That's why it is written f dash x plus some error which I have introduced, that error will be in order of delta x. So if we reduce the delta x, we can reduce the error, order of error also. So this is the mechanism. And if in the other case, in central difference and other thing, we also can see what is the order of errors. Here the order of error is delta x. And this error, this is already I mentioned, this order of delta x. Why delta x? So again I am explaining this delta, why delta x, because this term, so delta x whole square by 2 factorial into 1 by delta x f double dash x, this is neglected, so this is coming from here, and this term will be coming 1 by delta x cube by 3 factorial f triple dash x, etc. So this delta x and delta x square, 1 delta x is cancelled out. Here also delta x, so this cancel out 2. So maximum error occurred due to delta x present term in the neglected term, and in delta x square in the next neglected term. But delta x is much more than delta x square, because delta x is less than 1, much less than 1. So it can be written that or the order of delta x, this error is introduced. Now say another technique, not forward formulation, say centered formulation, because central difference, or it is called central difference technique. In a central difference technique, this is the central difference. As per the central difference techniques, del f del x is approximated as x plus delta x by 2 minus f x minus delta x by 2 by delta x. This also we have discussed in last class. So how much error, what is the order of error here? Again, let us start from the expression of the Taylor series expansion. This is actually plus minus delta x. Here also it is plus minus delta x. So this is the central difference technique, and you see from expression if x plus delta x by 2 minus f x minus delta x by 2 by delta x, how can you get this? If you put the value of delta x by 2 in the above expression instead of delta x, we can get the same thing. This will be delta x by 2, say. It is replaced by delta x by 2. If you replace this, this will give you the expansion in terms of delta x by 2. So f of x plus delta x by 2, and similarly f of x minus delta x by 2, you have to take these two equations and then you have to subtract. By delta x, it will be 1 by delta x into delta x f dash x plus delta x whole square by 3 factorial, and in this way it is going on. This is delta x 1 minute, delta x plus delta x by 2 minus delta x by 2 1 by delta x f dash x plus delta x square by 2 factorial term. Yeah, actually these terms, so even terms are cancelled out due to the subtraction of f x plus delta x by 2 and f x minus delta x by 2. So ultimately we are getting only the odd terms, odd factorial terms, that is delta x, f dash x, then f3 dash x, then f5 dash x, etc. All terms are not, because there is a term this minus this term. So some positive terms are cancelled out, so and negative terms are added. So ultimately this becomes delta x. So this will be, ultimately it is coming f dash x plus delta x square by 2. So first neglected term. So this is the first neglected term, and the next neglected term, this is of the order of delta xs square. This is cube term. This is the, there is a problem. This is a, so this is not a square term. So this 1 by delta x into these terms are coming, and if you divide these terms by delta x, the first term will become f dash x, and second term will become delta x whole square by 3 factorial. So ultimately the first neglected term is delta x square, and higher order neglected term will be proportional to delta x cube, etc. So first neglected term is delta x square. That means here the error is of the order of delta x whole square. So earlier in the forward difference technique we have seen it is error is in the order of delta x, and here it is of the order of delta x square. So of course delta x square is much less than delta x, because delta x less than 1. That's why in the central difference technique error is always less. So this is of the order of delta x square, and this first derivative for central difference technique method is more accurate compared to the forward difference technique. This is the summary. The centered scheme is more accurate. Now, what is the second order derivative? We have so far discussed the first order derivative, but what is the second order derivative? Again, if we start from the Taylor series expansion, say at x is equal to x0 point, x0 plus delta x will be f at x0. Say x is equal to x0, a particular point, x0 plus f delta x f dash x0 plus 1 by 2 factorial delta x square f double dash at x0. In this way it is going on. And similar, and x0 minus delta x will be just, these terms will be negative, and again third term 3 factorial term will be negative, another next is positive, then again 5 factorial term associated with the 5 factorial will be negative. In this way it is going on. Now how can I proceed? If we add these two terms, by adding these two expressions, f0 x f x0 plus delta x and f x0 minus delta x, so right side it will be twice of f x0, and these terms will be cancelled out, this plus and minus. So these terms will be cancelled out if we add these two terms. Similarly, the other term here associated with the cube, delta x cube, will be also cancelled out. So this twice f of x0 plus 1 by 2 factorial, that is 2 basically, 1 by 2. So into delta x square, so twice into this it will become delta x square f double dash x0 plus, suppose higher order term we are neglecting. What are the first neglecting term? First neglected term is in the order of delta x to the power 4. So first neglected term is associated with delta x to the power 4. So that's why the rest term we have written this is plus error. Error is the of the order of delta x to the power 4. So our intention is to calculate the f double dash x0. So f double dash x0, that will be left hand side minus twice f of x0 by delta x whole square. So it will be coming in this way. F double dash x0, it indicates f double dash x0, that is derivative, double derivative, that will be is equal to f0 x plus delta x plus fx0 plus fx0 minus delta x, left hand side minus twice fx0 divided by delta x whole square, and rest term we have neglected. And f double dash x0, ultimately this will be the formula I have written. By rearranging, there is minus twice f x0 is taken in the middle by delta x square. This is the formula for second order derivative, which is denoted by 116, equation number 116. These equation numbers are continuously given for your convenience. So this is equation number 116. In 115, up to 115 we have discussed in last class, there is forward difference and backward difference. This is the central difference formula for the, this is the formula for second order derivative, and first order derivative formula we have discussed in last class. So by using Taylor series expansion and approximation, we can have the formula for first order derivative, second order derivative, third order derivative in this way, and that will be used in a numerical solution. So this is the summary. Again, if we write, you see the equation number what I was mentioning, that this is del f del x is f of x plus delta x minus fx by delta x. This is forward difference technique. That is, you remember the forward side, that is plus direction, you are increasing x by x delta x plus delta x. Backward means you have to subtract the left side data, that is fx minus delta x by delta x, that will be backward difference. Both are first order derivative. And central difference, you have to go right side, x plus delta x by 2, also if x minus delta or delta x by 2, whatever it matters, if x plus delta x minus fx minus delta x by twice delta x is the central difference. Or if you like to write the delta x by 2, that is also valid. Then in that case, fx plus delta x by 2 minus fx minus delta x by 2, but in the denominator in that case it will be delta x, because this delta x is coming from this term, that is delta x by 2 plus delta x by 2. Actually delta x by 2 minus delta x by 2. In this way it coming delta x, because here we are incremental difference, we are considering delta x by 2. That can be also done. That means basically you are decreasing the incremental delta x, that is step size, half. Decreasing step size means more and more accurate result you are expecting. So these for three formulas for first order derivative, and for second order derivative this is the formula x0. Here also instead of x0 you can write by x also. In that case it doesn't matter. So in that case f double dash x will be, and approximation sign is there because we have truncated the Taylor series, we have approximated, we have discarded some terms. That's why that f double dash x, then no need to put the x0 value, then f of x plus delta x minus twice f x plus f of x minus delta x divided by delta x square. This also at a particular point, around a particular point x0, this formula then x0 will be coming. So this is also the equation 116. So these are the derivatives formula for the finite difference technique. Now, for application of these formulas to solve the equations for device, we have to divide the region of interest, that is the whole region of the device, by some grid structure. We have to divide it into a grid structure, and that is called meshing. So we have to generate some mesh. We have to divide the whole region into small parts of equal width. And suppose we consider a two-dimensional picture first. So a device, say two-dimensional analysis we want to do. Suppose we have a device like this. Say meshing, how we can do, you see, say this is a PN junction device where P silicon is the thick enough and N silicon is the thin. This is just like a crystalline silicon solar cell structure. You know the absorber layer is wider, much wider than the emitter layer. So this structure we have taken. Now we have to solve the device equations for this structure. How can you do that? There are two techniques of meshing. One is uniform meshing, another is non-uniform meshing. Meshing means we have to divide the whole region into small parts. How? We can draw some horizontal and vertical lines covering the device region, say in this way. So this is the division. So whole region, it is divided into small parts of equal width along x-axis, similarly along y-axis. Step size along x-axis and step size along y-axis may be different, but step size along x-axis, if this step size is equal for all the lines, then it is called uniform meshing, and in the figure it is shown uniform meshing. Another type of meshing is called non-uniform meshing. How it looks, let us see. Again, we consider the same structure, the PN junction structure, and if we like to divide this structure into non-uniform meshing technique, it will be like this. You see, here the grids are arranged in such a way that in the middle portion along x-axis, at the middle, these are closely spaced grids, that is closely spaced vertical lines. Similarly, in the top portion of the device, the horizontal lines are closely spaced. So this is not a uniform meshing. This is non-uniform meshing. It has specific advantage. I'll discuss. Actually, meshing, after meshing, we have to solve the device equation at each node. This is called mesh node. These are called mesh nodes. This is the mesh nodes. And if the boundary condition is given, say potential at the boundary at x is equal to 0, say, is given, and at x is equal to 0 and y is equal to 0. Suppose potential is given here. That boundary condition also you have to maintain, you have to in the solution. say this point is, suppose x is equal to 0, y is equal to 0. At this point, some potential, say phi at 0, 0, it is say given. Then this is say boundary condition. That boundary condition also you have to maintain. Other nodes, at other nodes you have to calculate the potential, electric field, charge density, that is carrier density, that is N and P, all. So for more and more accurate result, you have to increase the grids, number of grids or number of node points. That means you have to use the smaller and smaller grids. That is called finer mesh. More and more fine mesh. If you use fine mesh, you will get the more accurate result. But at the same time, it consumes more memory allocation or computer resources and also time. So if you increase the density of mesh or number of nodes, if you are increasing, then it will take more time, it will use more computer resources, but it will give the accurate result. But in non-uniform meshing, what we do, suppose we have idea about the device physics that near the junction there will be more and more physical phenomenon occurs. This is more important than junction points rather than a bulk point. That means the physics associated, physics in the physical phenomena in the bulk portion almost remain same. But near the junction there is a sudden change because electric field will change, potential will also be a different nature from the bulk. So near the junction, the depletion layer also will be formed near the junction. So near the junction, we need more accurate calculation. So in that case, we can increase the density of mesh near the junction by increasing the horizontal lines, grid lines covering the junction, as well as by increasing the vertical lines in the middle portion. But in this example, increasing vertical lines is not so important. Increasing the horizontal grid lines near the junction is more important. Also, suppose you have some contact. So finger-like contact. Here suppose you have some contact. These are the contact points. These are the also contact points. You know, in the contact there is a metal semiconductor interfaces are there. So near the contact also you like to increase the mesh. Then in this portion also you can increase the mesh lines. That means if we would use this dense mesh all over the device region, then it would need much more time and it would use the memory and computer resources more. So non-uniform meshing is one type of optimum solution. So the region of interest where more and more physical phenomena are expected, we have to increase the mesh density at those points. And in other points, we can have a low mesh density. So for accurate, but at the same time, using less memory and less computer resources and less time. So this is the purpose of non-uniform meshing. And the delta x, whatever I mentioned in the formula in this lecture, in previous slides, this delta x is nothing but the step size in position x. So this is delta x. So that is node point, one node point to next node point gap, that is delta x. Similarly, along y-axis, this will be delta y, that is small incremental change from one node to other node, the coordinate. So delta x and delta y. Is already I mentioned that small incremental change delta x between mesh points is constant in a uniform mesh and varies in a non-uniform mesh. And some advantages of non-uniform meshing already I discussed. There is a higher accuracy in critical regions. Critical regions means the regions where more and more physical phenomena are there. Say finer resolution where physical quantities like electric field, carrier density, some potentials, some carrier concentrations such as near the junctions or depletion regions are important. Similarly, sir, heterointerfaces also, heterojunctions. And it reduces the computational cost and also it improves the convergence and stability. And the mesh points, for notation we have to use some notations for the mesh points. That notation you have to be careful. We will be following this throughout the discussion. AI, that is delta x. Delta x is the distance between two mesh points in the x direction. That is xi plus 1 minus xi. That will be denoted as AI. I is equal to 0, 1, 2, 3, n in general, because I may be say x2 minus x1, x1 minus x0. So x0, it starts from x0. That is the lowest point. That is coordinate you can consider x0. So x1 minus x0, x2 minus x1 in this way. So x1 minus x0, that will be equal to x2 minus x1, that will be equal to x3 minus x2 is equal to say delta x in case of uniform meshing, of course. And bj, the another symbol we use to define the distance along y direction, delta y, that will be yj plus 1 minus j. J is now next another suffix, because to differentiate from I, that's why j is used. Similarly, y is 1 minus y0, y2 minus y1 in this way, that will be the bj. So b1 means y1 minus y0. ai means xi plus 1 minus xi. And bj is equal to yj plus 1 minus yj. So again I will clarify. So a0 will be x1 minus x0. So it depends on this value. So a0, that will be x1 minus x0. Similarly, a1, that will be x2 minus x1. And b0 will be y1 minus y0, but b1 will be y2 minus y1. Be careful. In this way, we will use the notation. Suppose we have a point like this, and if we draw, we can write in this way. Suppose you have a coordinate system like this is the central point. This point along y-axis, this is y, this is x point, and here you can mention that this is the point here, and you consider another point here, another point suppose here. So ai, this is ai, and this is ai minus 1. Similarly, this point, so this will be say bj, and another point here will be bj minus 1, and this half point, if we consider this is a half point, this will be I minus half comma j, and this is I minus 1 comma j, this point. This will be I plus 1 comma j. This point is I comma j, any point, and this will be I j plus 1. This will be I j minus 1, j minus 1, and so this middle point also you can see, this middle point, this will be I comma j minus half, and this will be, this point will be I comma j plus half. So also this half point, if there is any half point, this can be denoted as I plus half comma j. So these notations will be used for the discussion and solution. Also these notations, fxy will be fij. Xy, this point, ij means xy point. 0, 1, 2 will vary, I and j will vary, I will vary from 0 to n, j will vary from 0 to m, because maybe different grid points or mesh points along x-axis and y-axis. They may be different, they may be same also. And if x plus delta x y, that will be denoted as f I plus 1 j. So x plus delta x is I plus 1 j, next point. And if x plus delta x by 2 comma y, that will be f I plus half comma j. So if we divide the delta x increment by 2, this will be I plus half j. So we have discussed in this class, that is meshing techniques to solve the device equations at the each points of the grid structure, and what is the advantage of non-uniform meshing, that is also discussed. And in the next class we will do some discretization technique based on the notations discussed in this class. It's the reference. Thank you.